So this next discussion goes with model fitting, and what this is really looking at is trying to determine how many predictor variables I need to have in my final multiple linear regression model. And so I have three processes that are considered iterative processes, which means that at each step of the procedure, I either add or remove an individual independent variable and look at how the model adjusted when I made that change. Another way that we can do this is by using the best subsets procedure, which happens when we look at the different regression models based on different subsets of independent variables. And so the first thing that we're going to look at is our forward selection procedure. So we have an analyst that establishes a criterion for allowing independent variables to enter the model. And so we have an example where the independent variable j with the smallest p-value associated with the test of the hypothesis of beta sub j equals 0, subject to some predetermined maximum p-value for which a potential independent variable will be allowed to enter our model. So with forward selection, the first step is going to be the independent variable that best satisfies that criterion is added to our model. And then every step after that, the remaining independent variables not in the current model are going to be evaluated, and the one that best satisfies the criteria is then added to the model, one step at a time. And this will continue going until there are not any more independent variables that aren't in the model that still meet the criteria for being added to our regression. We have backward selection. So the analyst is going to establish a criteria for allowing independent variables to remain in the model. So the example is the largest p-value associated with the test of the hypothesis of beta sub j equals 0, subject to some predetermined minimum p-value, typically 0.05, for which a potential independent variable will be allowed to remain in the model. And so we're going to go backwards, right? So that first step, we look at the independent variable that violates this criteria and we take it out. And every time we take one out, we reevaluate the model. And we continue doing this until none of our independent variables currently in the model continue to violate the criteria for remaining in our regression model. We also have stepwise procedures. So when you do a stepwise procedure, the analyst is going to set criteria for both allowing variables into the model, but also allowing variables to remain in the model. So in that first step of the procedure, the independent variable that best satisfies the criteria for entering the model is added. And first, the remaining independent variables not in the current model are going to be evaluated, and the one that best satisfies the criteria for entering is then added into the model. But then, the independent variables in our current model are going to be evaluated, and the one that violates our criteria for remaining in the model to the greatest degree is then taken out. And the procedure will stop when I don't have any more independent variables not currently in the model meeting the criteria for being added, as well as not any of our independent variables currently in the model violating the criteria for remaining in our regression model. When we do the best subsets procedure, basically a simple linear regression for each of the independent variables under consideration will be made, and then the multiple regressions with all the combinations of two independent variables under consideration are made. Once a regression that has been generated for every possible subset of our independent variables under consideration has been made and evaluated, we then get an output that provides some criteria for selecting the regression model, and that's going to be generated by your statistical software. One of the concerns that we have when we fit models is something called overfitting. And this is going to result from making your model too complex. And so if you spend a lot of time putting a lot of variables into your model that's going to explain all the nuances in your data, you end up with a really complex functional form or independent variables that don't have a meaningful relationship with that dependent variable. And if your model is overfit to your sample data, it's really not very useful when you bring in new data from your population. Remember, the whole point of making the model from your sample is so that you can then generalize it to the greater population. So if it's overfit to your sample, you can actually end up with some really misleading results about the predictive capability and the interpretation as it pertains to making generalizations about your population. So how do we avoid overfitting, right? So you're only going to use as many independent variables as you absolutely need. So things that you expect to have a meaningful relationship. Now this goes back to that discussion earlier about if you keep a predictor variable in your multiple linear regression, maybe it wasn't statistically significant, but you do have an a priori reason for keeping it in there, right? So if it makes absolutely no sense to have the two variables um, in relationship with each other, then take it out. Sometimes you might want to use complex models like a quadratic model or a piecewise linear regression model. But you can do that when you have a reasonable expectation that that level of complexity is going to provide you a more accurate picture of what you're looking at. And one of the big things to pay attention to is don't let your software tell you what to do. Use your iterative modeling procedures such as stepwise, best subsets, and so forth, only for guidance to help you figure out what that final model is. But really, at the end of the day, it is your responsibility to make the interpretation. The computer is only going to do what you tell it to. So if we're looking at model fitting, we have our full data set and we split it into our training and test set. And our training set then gets split into a training and validation set. So if you have access to enough data, you want to assess your model on the data other than your sample that was used to generate your model. And so this is going to be called cross-validation. And it's recommended that you divide your original sample data into your training set and your validation set. So your training set is the set that you use to make your model. And that's going to build the candidate models that appear to make practical sense. Your validation is going to be the data that you use to compare your model performances together. And ultimately, you'll end up picking a model for predicting values of your dependent variable. So if you have a testing set, then you actually do your final level of comparison there. Typically, when you have regular sized data sets, you're only going to really have your training and your validation set. So oftentimes you do your model comparisons based on your validation data. But if you have a testing set, then you need to do your evaluations based on your testing set. So, for example, we might randomly select half of the data for use in developing our regression model. Then we could use the data as our training set to estimate a model or a collection of models that appear to perform pretty well. And then we can use the remaining half of the data as a validation set to assess and compare the model's performance and ultimately select a model that minimizes some measure of overall error when you apply it to your validation set. So some different methods that you can use with model fitting. We have holdout method, where you basically take your sample and you randomly divide it into different groups of training and validation. So mutually exclusive means that you can only belong to one group, and collectively exhaustive means that everybody in your data group is assigned to be in either the training or validation set. K-fold cross-validation is where you take a sample of your data randomly divided into however many groups that you want to be. So K equally sized. Once again, mutually exclusive, collectively exhaustive. So only in one group, and everyone's got to be in a group. And we call these folds, and we end up with however many iterations of our evaluation of your model based on however many folds you have. Another one we have is leave one out cross-validation. It's very similar to K-fold cross-validation. The difference is that you have n minus one folds. So basically when you're dividing your data set up, it's everything but one observation. So for a sample of n observations, an iteration is going to estimate your model on all of them but one. And it's going to evaluate the model on the single observation that was omitted from your training data.